most probable value. What is this? We know in quantum mechanics, a particle is a wave packet like this one. Here you can see the particle is spreaded over a certain region, that is we call delta x, that is uncertainty in position. So the particle can be anywhere in between this delta x position, that is particle can be at this location or anywhere inside this wave packet, right? And for observing the particle at each position have certain probability. Here we have to find out the most probable value, that is for this wave packet you can easily see the maximum probability of finding the particle will be at the center, at the middle. Okay, because the density value, that is mod psi square value, will be maximum at the middle for this case. So here in this case we represented the particle by a graphical method, but in general we use mathematical expression for the particle, that is wave function psi. So in a problem usually they will give a wave function psi and they are asked to find out the most probable value of finding the particle. Then how we can solve this kind of problems? Here what we have to find out? We have to find out the probability density. The location where the probability density is maximum. Therefore, first we have to find out the location where the probability density is maximum. If we got that location, then substitute that value in the wave function, so we get the most probable value. Therefore, the first step is we have to find out the location where the density is maximum. So to find out this one, we have two conditions. One is 1D case and the other is 3D case. We need to use two different equations for solving this problem in two different dimensions. For 1D case, we have to take the derivative dou by dou x of mod psi square and we have to equate this value to 0. And for 3D case, this equation is little different, that is dou by dou r of mod psi square r square should be equal to 0. So we have to equate these derivatives to 0, then we can find out the r value. Then we resubstitute this r value in the expression for psi. Then find out the mod psi square, then we get the most probable value. Okay. One example problem. Let us consider a 1D box. A 1D box of length 0 to L. And I am considering a wave function equal to root 2 by L sine pi x by L. This is a ground state wave function, so it will look like this one. Now the question is, we have to find out the most probable value. How we can find out? Here this is a 1D problem. So how we solve? We have to take the derivative of wave function and we have to equate it to 0. Here what we get, that is dou by dou x of mod psi square, that is 2 by L sine square pi x by L is equal to 0. So what we get? Here we get 2 by L. Derivative of sine square pi x by L is 2 sine pi x by L into derivative of sine pi x by L, that is cos pi x by L into derivative of pi x by L, that is pi by L. That is equal to 2 by L into pi by L into 2 sine theta cos theta is sine 2 theta, that is sine 2 pi x by L, and this should be equal to 0. For this condition to be satisfied, the x value should be equal to L by 2. When we are substituting this value here, we get sine pi. Sine pi is 0. Okay, so x equal to L by 2 is the position where this wave function have maximum probability density. And that condition you can obviously see from this figure. See, this is the position L by 2. And at this position, the wave function have maximum value probability density. Okay. So by using this equation, we can find out the position where it have maximum probability density. Right. Now what we have to do? We have to substitute this value x equal to L by 2 in our wave function. Then we can find out the probability density at that location. Now we are going to do that one. Here this is our 1D box of length 0 to L, and this is our wave function, and it have maximum probability density at the L by 2, right? And this wave function is root 2 by L sine pi x by L. Now I have to find out the wave function at x equal to L by 2. That is, we have to substitute for x value, that is root 2 by L into sine pi by L into x. X is L by 2. So what we get? We get this is equal to psi at x equal to L by 2 is equal to root 2 by L sine pi by 2, right? L will cancel and sine pi by 2 is equal to 1. So this is the wave function at x equal to L by 2, where x equal to L by 2 is the most probable position for the particle to be seen. Okay. So from this wave function, we can find out the probability density, that is mod square, that is equal to 2 by L. So this will be the most probable density for the given wave function. Okay. Another example, wave function size given, that is equal to 1 by root pi a0 cube e raised to minus r by a0. This is the wave function of electron in first orbit of hydrogen atom. And here the question is to find the most probable value. Value of electron. How we can find out? We have to take the derivative of probability density and equate that value to 0. But here you see this is a 3D case, because this wave function represents the electron cloud around the hydrogen nucleus. So which equation we will use? We will use dou by dou r of mod psi square r square equal to 0. That is what we get, dou by dou r of r square into mod psi square, that is 1 by pi a0 cube e raised to minus 2r by a0. And we have to equate this value to 0. So what is this derivative? We can take the 1 by pi a0 cube outside, and derivative of dou by dou r of r square e raised to minus 2r by a0 equal to 0. So what we get? That is equal to 1 by pi a0 cube into derivative of first function, that is 2r into e raised to minus 2r by a0 plus r square into derivative of second function, that is e raised to minus 2r by a0 into minus 2 by a0, that is equal to 0. Here we can multiply this equation by pi a0 cube on both sides. Okay, so this will cancel, and here also we again get 0 value, right? And I can take 2r as a common term. So I can rewrite this as 2r into 1 minus r by a0 into e raised to minus 2r by a0 equal to 0. This condition will be satisfied if r equal to 0 or this entire term is equal to 0. So there are two conditions. One is r equal to 0 and other condition is 1 minus r by a0 equal to 0, that is r equal to a0, right? So the probability density will be maximum at these two locations. One is r equal to 0 and other is r equal to a0. Now we have to find out the corresponding wave function at these locations. That is, given wave function psi is equal to 1 by root pi a0 cube e raised to minus r by a0. Now we have to find out the wave function at r equal to 0. That is, we have to substitute r equal to 0 in this equation, right? That is equal to what we get? We get 1 by root pi a0 cube. But here there is a problem, because I told you this wave function represents an electron cloud in the hydrogen atom. And what is the meaning of r equal to 0? That is, at the location of nucleus, there is a electron wave function. That is, at the nucleus, there is electron. But this is not logical, right? Because at the location of nucleus, there will not be any electron. Therefore, this solution have no physical significance. So we neglect this result. And now we have to check the other condition, that is wave function psi at r equal to a0. What we get? We get 1 by root pi a0 cube e raised to minus 1. From this equation, you can easily find out the probability density. Then you will get most probable value of finding the electron at the location r equal to a0. Here r equal to a0 is the location where maximum probability of finding the electron. Okay. Expectation value. I think you are familiar with the eigenvalue equation. That is, some operator is acting on a wave function. So it will give an eigenvalue and a wave function. So here I tell you an analogy to understand this eigenvalue equation. Here this O cap is an operator. Suppose this is a temperature measurement tool, that is a thermometer, and the wave function, that is a state, and suppose we are consider it as a bucket of water. So we are using a thermometer to measure the temperature of water. So what we get? We get the temperature value, and the bucket of water will be definitely will be remaining, right? So that is this eigenvalue equation. We are doing a measurement on certain system. After measurement, it will give the measured value and the system as itself. Okay, so that is this eigenvalue equation. And this expectation value is defined as, we are multiplying this eigenvalue equation once again with the conjugate wave function, that is psi star operator psi equal to psi star lambda psi, where this lambda is a scalar quantity. Okay, so we can take it outside, that is psi star operator psi will be equal to lambda psi star psi. Now the expectation value of operator is defined as integral of psi star operator psi dx divided by integral psi star psi into dx. If the wave function is normalized, then we get this integral value as equal to 1. By doing this integration, we get this lambda value. That is the measured value. So this is the equation for expectation value. Expectation value is nothing but average value. Let us consider a quantity A. So this A is how certain variation. So this is a quantity A. Now I am going to find out its expectation value, that is its average value. So what we get? We get a line like this, right? So this is average A. And here you can easily see there is a difference between the real quantity A and its average value. And we can find out its RMS value of deviation. That is, R means root, M means mean, S means square. That is, root means square of deviation. That is root of mean of square of deviation. That is deviation of the quantity, this one, right? That is A minus average A. So this is RMS value. What is this RMS values giving? The uncertainty, right? So this is nothing but uncertainty in delta A, in the quantity A. That is uncertainty in the quantity A. That is equal to root of mean of A minus average of A all square. So I can do some mathematical manipulations. That is, I can square these terms. So what we get? We get delta A is equal to root of average of A square minus 2A average of A plus average of A all square. So I can take this averaging into all these quantities. So what we get? We get delta A is equal to root of average of A square minus 2 average of A into average of A plus average of A all square. That is what we get. We get delta A is equal to root of average of A square minus average A all square. This is the expression for uncertainty in a quantity. Suppose you have to find out the uncertainty in position, that is delta x. Then what you have to do? You have to find out this one, RMS value of it, that is average of x square minus average of x all square. If you want to find out uncertainty in momentum, then you have to find out root of p square minus average of p all square. That is, suppose a wave function is given, then what you have to do? You have to find out psi x psi. So you get expectation value of x. And to calculate this delta x, you have to find out psi x square psi, that is average of x square or expectation value of x square. So if you have this value and this value, then substitute in this equation, then you can find out the uncertainty in position. And in integral form, the expectation value of x is equal to psi star x psi dx, and the x square is equal to integral psi star x square psi dx. So these are the integral form. So by doing this integration, you can find out the expectation value of x and x square. Then also you can find out the delta x, that is uncertainty in position. Example problem. A particle is there in a 1D box of length L. Here this particle is in a infinite potential well. So inside this box, potential of the particle is 0. And the wave function is given, that is psi n is equal to root 2 by L sin n pi x by L. The question is to find out uncertainty in position. That is, we know delta x, that is uncertainty in position, is equal to root of average x square minus average x whole square, or expectation value of x square minus expectation value of x whole square, right? So first we have to calculate this one, then we have to calculate expectation value of x square. So what is this expectation value of x? That is equal to integral psi star x psi dx. Here the particle is in the region 0 to L, so the limit will be 0 to L, and we know the wave function psi, that is psi is equal to root 2 by L sin n pi x by L, and psi star also will be the same one, right? Because there is no I terms, so the complex conjugate of this wave function will be same. Okay, so we have to calculate expectation value of x, that is integral 0 to L psi star, that is same one, that is 0 to L 2 by L sin square n pi x by L into x dx. That is equal to, I can take this 2 by L outside, 2 by L into 0 to L x into sin square n pi x by L dx. Here we can do the integration directly on sin square n pi x by L. So we have to rewrite in another form, that is, we know sin square theta is equal to 1 by 2 into 1 minus cos 2 theta, that is 1 minus cos 2 n pi x by L. Now we can rewrite expectation value of x is equal to 2 by L into 1 by 2 integral 0 to L x into 1 minus cos 2 pi x by L into dx. Again, I am going to rewrite this equation, that is expectation value x is equal to, here we can cancel this 2 and 2, so we get 1 by L into integral 0 to L x dx minus integral x cos 2 pi x by L dx, 0 to L. Okay, so here what we get? We get 1 by L into integral of x is x square by 2 and limit is 0 to L, minus what is integral of this term. Here this integration is little difficult, so I tell you a trick to solve this kind of integral. Here what is this first term? That is x. I am writing this x value here, and what is the second term? That is cos 2 pi x by L. I am writing it here, and what I am going to do is I am going to take derivative of this term x. So what is the derivative of x? It is equal to 1. And I'm taking its derivative once again. So what we get? 0. And again taking derivative, we get nothing, 0, right? So I'm stopping this derivation up to 0. And there is no more derivation. Okay, and I'm going to take integration of this term. So what we get? First integral of this one, we will get sine 2 pi x by L into L by 2 pi. Okay, and again integrate this function. So we get L by 2 pi or square, that is minus will be there, and cos 2 pi x by L. Now what I'm going to do is I'm going to multiply these two times and these two times. And when multiplying, I'm taking this term as positive and I multiply this term with a negative sign. So I can rewrite this expression as this one, that is L by 2 pi x sine 2 pi x by L, where the limit is 0 to L, minus, here there is a minus and here also one minus is there. So this will become plus L by 2 pi or square into cos 2 pi x by L, where the limit is 0 to L. So integral of this function we will get as this one. Now we can substitute for these limits. Then what we get? If you substitute these limits for the first term, we get it is equal to 0. And if you are substituting for the second term, again we get 0. That is the integral of this entire term is equal to 0. Okay, so we got this expectation value of x as this one. That is, we get expectation value x is equal to 1 by L into L square by 2. So we get expectation value of x is equal to L by 2. Now we have to find out expectation value of x square, right? Because we know delta x is equal to root of x square minus expectation of x whole square. Now we have to find out expectation value of x square, that is equal to integral 0 to L x square into psi star psi, that is 2 by L sine square n pi x by L dx. So here I can take this 2 by L outside the integral, that is 2 by L integral 0 to L x square sine square n pi x by L dx. Here we have to rewrite sine square n pi x by L in another form, that is 1 by 2 into 1 minus cos 2 n pi x by L. Now we can substitute this value here. So we get expectation value of x square as 2 by L into integral 0 to L x square, here 1 by 2 I missed, x square into 1 minus cos 2 n pi x by L into dx. That is, expectation value of x square is equal to 1 by L into integral 0 to L x square dx minus integral 0 to L x square cos 2 n pi x by L into dx. Here also we can use the earlier trick to solve this integral. What is the trick? We have to write this square here and we have to write this term here, that is cos 2 n pi x by L, and we have to take derivative of this term and take integral of this term, that is derivative of x square is 2x, and again we have to take its derivative, so we get 2, and again take its derivative, we get 0. And now for this term we have to take integral, that is we get L by 2 n pi into sine 2 n pi x by L, and again take its integral, we get minus L by 2n pi all square cos 2n pi x by L, and again take its integral, we get L by 2n pi all cube sin 2n pi x by L. Now we have to multiply these terms. So for first term we have to take plus sign, for second term we have to take its minus sign, and for third term we have to take again the plus sign. So what we get? We get L by 2n pi x square sin 2n pi x by L, limit 0 to L, and minus and minus, it will be plus L by 2n pi all square into 2x cos 2n pi x by L, limit 0 to L, plus L by 2n pi all cube into 2 into sin 2n pi x by L, limit 0 to L. On substituting this limit, we get this term equal to 0 and this term also equal to 0. So the remaining term is this one only, right? So what will be its value? That is L by 2n pi all square into 2. Now we have to substitute the upper limit, that is L into cos 2n pi x by L. So when we are substituting this L will cancels, and we get cos 2n pi, that is equal to 1. Now we have to substitute the lower limit, that is minus 0, right? So we get this is equal to 2L into L by 2n pi all square, that is L cube divided by 2n square pi square. This is the value of the second integral, right? So we get expectation value x square is equal to 1 by L into, from the first integral we get the value L cube by 3, and second integral we got this value, that is minus L cube by 2n square pi square. That is expectation value of x square is equal to L square by 3 minus L square by 2n square pi square. Now we can find out the delta x value, that is delta x is equal to root of x square minus expectation value of x or square. So this is a work for you. You please substitute these values here and find out the delta x. Distribution function. Distribution function rho is nothing but probability density. That is, we know probability density is psi star psi, or it is equal to mod psi square. The same thing is called distribution function rho, because you know the probability density is distributed over a certain region delta x. So we can call it as a distribution function also. Suppose in a problem they are specified a distribution function, then how we can find out expectation value? We know what is expectation value? It is equal to integral psi star psi x dx, that is equal to integral rho x dx, right? And what is for x square? That is equal to psi star x square psi dx, that is equal to integral rho x square dx, because we know psi star psi is distribution function. One example problem. Distribution function is given, that is equal to a e raised to minus lambda x square, and the question is to find out expectation value of x and the x square. What is this distribution? This is a familiar function. This is Gaussian distribution. And here this distribution function is not normalized. So before solving for expectation value of x and x square, we have to normalize this distribution function. How we can normalize? What is the normalization condition? Now we have to integrate it from minus infinity to infinity, a e raised to minus lambda x square dx, then it should be equal to 1. And I already told you a trick to find out the value of this integral. Therefore, we get this is equal to a into root pi by lambda is equal to 1. That is, the trick is, I told you, integral minus infinity to infinity e raised to minus ax square dx, then this will be equal to root pi by a. So here in this question, in the position of a, lambda is there. So we get a into root pi by lambda is equal to 1. So we can find out a value that is equal to root lambda by pi. So the normalized distribution function is root lambda by pi e raised to minus lambda x square. Now we can calculate expectation value of x, that is equal to integral x rho of x dx, that is equal to integral minus infinity to infinity. We can take this constant outside the integral, that is root lambda by pi into x into e raised to minus lambda x square dx. Here you can see this function is an odd function and this function is an even function, and we are integrating this from minus infinity to plus infinity. So here the product of this function is odd function. So when we are integrating it from minus infinity to plus infinity, we get a value 0. So expectation value of x is equal to 0 for this distribution function. Now we can find out for x square, expectation value of x square, that is equal to minus infinity to infinity x square rho of x dx, that is equal to root lambda by pi integral minus infinity to infinity x square e raised to minus lambda x square dx. Here I tell you an important formula to solve this kind of integral, that is integral minus infinity to infinity x raised to 2n e raised to minus ax square dx, then it will be equal to root pi 1 into 3 into 5 etc. 2n minus 1 factorial by 2 raised to n a raised to n plus 1 by 2. This is a very important formula to solve this kind of integrals. So by using this equation, what we get for x square? It is lambda by pi into integral of this function. Here n value is 1. So what we get? Root pi into 1 into etc. 2n minus 1 factorial, that is n is equal to 1. So it is 1 factorial up to 1 factorial. That is the maximum value is 1 factorial. So this is only 1 by 2 raised to 1, that is 2. Here in the position of a, lambda is given. So lambda raised to n plus half. Here n is equal to 1 plus half. So we get expectation value of x square is equal to, here this root pi and root pi will cancels. So finally we get 1 by 2 lambda.